Welcome. Let's take a look at an introduction to quadric surfaces. Let's go ahead and start with a definition of what a quadric surface is. It's any surface that is the graph of an equation in this general form: ax squared plus by squared plus cz squared plus dxy plus exc plus fyz plus gx plus hy plus iz plus j, where all of these coefficients a, b through j are constants. When a quadric surface intersects a coordinate plane, that trace or curve created in the coordinate plane is referred to as a conic section. In this introduction, we are only going to be focusing on the case where the coefficients a, b, and c are non-zero, and j. J might be 0, it might be another constant. So let's go ahead and get started. Now, based on this definition of quadric surfaces, there are 6 basic types: the ellipsoid, the hyperboloid of one sheet, the hyperboloid of two sheets, an elliptic cone, an elliptic paraboloid, and a hyperbolic paraboloid. The degree and the signs of coefficients and which terms are present in the equation help determine which of these basic surfaces is given. So we're going to go ahead and take a look at each of these 6 basic surfaces. So if the need for graphing one of these surfaces by hand is necessary, there are a variety of tools that can be helpful. For example, the intercepts in the x, y, and z axes, traces in the various coordinate planes, and level curves can be helpful. So let's start by looking at the ellipsoid. The ellipsoid has an equation of the form x squared over a squared plus y squared over b squared plus z squared over z squared over c squared equals 1. Some things to note about the equation itself is all 3 second-degree terms are present. All 3 second-degree terms are positive, and provided the equation is equal to 1. Notice that all 3 traces are going to be ellipses, and we'll take a look in a moment. And note that because of the structure of this equation, the intercepts of the coordinate axes are plus or minus a, 0, 0, 0 plus or minus b, 0, and 0, 0 plus or minus c. Here we have the graph of an ellipsoid. We've got x squared over 1/4 plus y squared over 4 plus z squared equals 1. And so this is an image of that particular ellipsoid. And so, for example, if we look at the graph in the YZ plane, notice we see an ellipse. And notice that the intercepts for the y-axis are at -2, 0, 0 and at 2, 0, 0. The intercepts for the y or the z-axis are at -0, 0, -1 and 0, 0, 1. Let's go ahead and take a look at the xy plane. Notice now that we can see that, again, we can see that the y-intercepts are at 0 plus or minus 2, 0. We can also see that the x-intercepts are at plus or minus 1/2, 0, 0. And no matter what perspective we take, even if we take the xz plane, we still have an ellipse. Next, we have the hyperboloid of one sheet. The form of its equation is x squared over a squared plus y squared over b squared minus z squared over c squared, and that is when it's equal to 1. Notice again that all 3 second-degree terms are present, and that 2 of those terms are positive, while the 3rd term is negative. Of course, this is provided the equation is equal to 1. So what happens is in one trace in this case the xy plane, we have an ellipse, and the other two traces are hyperbolas, and we'll take a look at that in a moment. There is an axis at the center of this surface, and that is parallel to the coordinate axis of the variable that is negative. In this case, the z variable is negative, so that center axis is the z-axis. In this particular example of a hyperboloid of one sheet, the intercepts of the coordinate axes are at plus or minus a, 0, 0, and 0 plus or minus b, 0. And note that there is no intercept of the z-axis. So let's take a look at this surface. Now we're looking at the graph of a hyperboloid of one sheet, and this particular hyperboloid is x squared over 4 plus y squared over 1/4 minus z squared equals 1. Notice that the z squared term is the negative term, and so there will be no z-intercept, and the center axis of the hyperboloid is going to be the z-axis as well. So let's take a look at some of the traces or the curves formed in the coordinate planes. So let's go ahead and turn this way so that we can see the zy plane. And when we do that, we can see that we have a hyperbola formed in the zy plane. If we turn and look at the y plane, notice we have the ellipse that we were anticipating. And now as we look in the xz plane, we can see the beginnings of another hyperbola. Notice that it is a horizontal hyperbola, whereas the yz plane was a vertical hyperbola. Now to look at the hyperboloid of two sheets. Notice in this particular equation that all three second-degree terms again are present. Notice though that in this case, two of those terms are negative and one is positive. That of course is provided that the equation is equal to 1. Similar to the hyperboloid of two sheets, two of our traces in the coordinate planes are hyperbolas, and one of the level curves will be an ellipse parallel to the third coordinate plane, and we'll take a look at that. The axis at the center of the hyperboloid is parallel to the coordinate axis of the variable that's positive. So in this case, our variable z is the positive variable, and so notice that the z-axis is an axis at the center of this surface. In this particular example, the intercepts of the coordinate axes are 0, 0, plus or minus c, and there are no x or y intercepts. So let's go ahead and take a look at this surface. Here we have a hyperboloid of two sheets. The equation here is negative x squared minus y squared over 1/2 plus z squared equals 1. And notice that this surface does in fact come in two parts. Notice there are no x and y intercepts, but we do have two z intercepts. And those z-intercepts will occur at 0, 0, negative 1 and 0, 0, 1. So let's look at the traces. So if I look at the YZ plane, I can see the formation of a hyperbola, and a vertical hyperbola. If I look at the XZ plane, I can also see the formation of a hyperbola. Notice in this case, both hyperbolas are vertical hyperbolas. Thirdly, we get the formation of an ellipse if we take a level curve. So imagine that I'm cutting through this surface at z equals 3. z equals positive 3. So that would be where we see this surface artificially end. So let's go ahead and take a look from the top vertically down to see what kind of curve is created when I chop my surface here at the z equals 3 level. So when I do that, notice that this outer curve, which represents when z was equal to 3, does in fact form an ellipse. The next surface let's look at is the elliptic cone. Notice the difference in this equation to the previous equations. Notice that rather than the right-hand side being 1, our right-hand side is 0. So all three second-degree terms are present. 2 of the second-degree terms are positive, while the third is negative. And of course, that all assumes that the right-hand side, or the equation, is equal to 0. So in this case, 2 of our traces will be hyperbolas, and one of our level curves will be a point, for example, here at the origin, or an ellipse parallel to the third coordinate plane. In this image here, an ellipse parallel to the xy plane. There's an axis at the center of the cone, and that is parallel to the coordinate axis of the negative variable. Our z variable is negative, so in this image we have the center axis being the z-axis. In this particular example, there is only one intercept of the coordinate axes, and that occurs at the origin. So let's go ahead and take a look at this cone. Here we have an elliptic cone. Its equation is x squared plus y squared over 1/2 minus z squared equals 0. And so we can see we have this cone shape. We can see there is only one intercept here at the origin. Let's go ahead and take a look at the trace in the YZ plane. And our trace here is forms of hyperbola. Let's go ahead and take a look at the XZ plane. And again, our trace here is a hyperbola. And then let's go ahead and look at a level surface. So this top piece of the surface we're seeing here, our our cone is chopped off at the level of z equals 3. So when we look down on this along the z-axis, we will see what the level curve for z equals 3 looks like. So doing that, we can see that in the xy plane, or parallel to the xy plane, so this level curve at z equals 3 forms indeed an ellipse. Next we have the elliptic paraboloid. Now notice that we do not have all second-degree terms present. We have 2 second-degree terms and 1 first-degree term present. Now, the traces of this shape in 2 of the coordinate planes is our hyperbolas, and one of the traces is an ellipse. So we have an axis at the center of the paraboloid, and that is parallel to the direction of the first degree variable, in this case z. So our axis is z. And in this example, the intercepts of the coordinate axes in this particular example is simply the origin. So let's go ahead and take a look at an elliptic paraboloid. Here we have the graph of the elliptic paraboloid, z equals x squared plus y squared over 4. Notice that this elliptic paraboloid seems to have a bowl-type shape. We know that it has an intercept at the origin. And let's go ahead and take a look at the traces in the coordinate axes. So if I look at the trace in the, there we go, in the xz plane, notice that I'm getting an ellipse. If I go to the YZ plane, Notice I'm also getting ellipse. And then this particular surface I have cut off at z equals 3 so that we can see the level curve of this surface at the level z equals 3, and it should form an ellipse. So if we look downward along the z-axis at this surface, whoops, this curve here we can see is an ellipse. So the level curve of this elliptic paraboloid is in fact an ellipse. And now we have our final surface, the hyperbolic paraboloid. Note the equation has two second-degree terms, but one of them is positive and one is negative, and one first-degree term is present. Now, there are two traces of this surface that will be parabolas, and one trace that will be a hyperbola. There is an axis at the center, and that axis corresponds to the first degree variable. In this case, the z variable is first degree, so the z-axis is the center. And as far as intercepts go, this basic hyperbolic paraboloid has a single intercept at the origin. Sometimes we can imagine this hyperbolic paraboloid looking somewhat like a saddle. So let's go ahead and take a look at an example. So here we have the hyperbolic paraboloid, z equals negative x squared plus y squared over 4. And notice that there is this single intercept of the coordinate axes at the origin, and that the z-axis is the center axis of the shape. Now, we know that there should be two parabolas, one when we look at the traces in the coordinate planes. So let's go ahead and look at the here. And in the YZ plane, we have this parabola opening up, and it corresponds to letting the x coordinate equal 0. So we're seeing, in essence, the graph of z equals y squared over 4. Now let's look at the XZ plane right here, and notice that we have a parabola opening down, and the XZ plane corresponds to y equaling 0. So we have this parabola here that is z equals negative x squared. Now we did say that we expect one of the traces to be a hyperbola. So let's look down along the z-axis at our shape. And here we see, a hyperbola being formed in the xy plane. I hope you find this general overview helpful.